So now let's talk about how we actually find the solutions to linear systems. We're going to first look at homogeneous linear systems. We will also look at non-homogeneous, but let's first look at homogeneous linear systems. X prime equals a to the x is the system we want to solve. We're going to kind of do similar things that we did when we solved systems, just regular equations. Y prime, y double prime equals something times x or times y. We're going to actually do this using kind of the idea of we're going to suppose the solution is of the form x equals k e to the lambda t. And what that gets us is just as before, we're going to get our, we call it an auxiliary equation. Here we're going to call it slightly different. We're going to call it a characteristic equation. And the characteristic equation is, again, where we're going to plug this in. So we're going to take the derivative of this. The derivative of this, of course, is lambda times k e to the lambda t. So we're going to have lambda times k e to the lambda t. That's what the x prime is equal to. And that's going to equal a times my x, which was k e to the lambda t. I do want to point out one thing about matrices is you can't multiply in any order. So we do actually want to write this as a first because a was first in my a times x. So you can't just put them in any order you want to. You do need to put them in this order. Multiplication of matrices is not commutative. If I were to take this and realize that this could actually be thought of as a times k minus lambda times k, all times e to the lambda t equals the zero matrix. The zero matrix, by the way, is just a matrix that has all zeros. So it all works out beautifully for us. E to the lambda t, of course, is just a constant. It can't actually, not constant, it's just, in this case, it's not a matrix, it's just a scalar. It can't equal zero, so we can actually get rid of it. So we get a times k minus lambda times k equals the zero matrix. I would like to factor out, I notice both these have a k in them, I would like to factor that out. But one thing to remember with matrices is it's not as simple as just to factor out a one. We need to think about what is the one for a matrix. The one for the matrix is known as the identity matrix. The identity matrix has one down the diagonals and zero everywhere else. So it looks like that. A 3 by 3 identity matrix would be 1 0 0 0 1 0 0 0 1. The identity matrix, if you multiply it by a matrix, you get back the matrix you started with. So the identity matrix times k would give you k back. That's important because we actually want to think of this is a times k minus lambda I times k equals the zero matrix. That means I can actually pull out that k. So what this allows me to do is realize that I can pull that matrix k out, and we get that we get a minus lambda I times k equals 0. We then want to look at the fact that the only way that this actually could equal 0 is if we could actually think of it as kind of dividing by it. And so what we want to do is we want to not really divide by it, because you really don't do that, but we want to think about finding the determinant of it. So for non-trivial solutions of k, the determinant of a minus lambda I is not zero. Oh, I'm sorry, is zero. Is zero. Okay. So what we're going to do is we're going to look and trying to solve for this and find out what this is equal to. lambda is kind of going to be this kind of coefficient that's involved in this. We actually give a name to that. We call them eigenvalues. And I realize we saw eigenvalues other places in this class already. They're kind of similar, though they're kind of different. So this is our eigenvalue we're going to have. And when we do this, we will have that x is equal to k times e to the lambda t is a solution of if, I should say, if K is not the zero matrix itself. This is known as an eigenvector. So this K is your eigenvector corresponding to that eigenvalue. All right, we're going to go ahead and look at how we find these out using this kind of idea of what these look like. And we're going to use first case is going to have distinct eigenvalues. So x is going to be c1 times k1 e to the lambda t plus c2 times k2 e to the lambda t plus all the way through all these. We're going to start off with just a 2 by 2 and see what the solution looks like for this. So my first step to solve this is to first write this as a matrix. So if we want to write this as a matrix, the x matrix, remember the x matrix is the matrix xy. You can do x1, x2, but since we're using x and y, we use xy. And so this would be x prime is equal to the coefficients minus 5, 2, minus 5 halves 2, 3/4, negative 2 times that matrix x. All right, so we have that written in that format, and we now can think about what we're going to do. We do want to look at this determinant of A minus lambda I. Remember, I is the matrix that has 1 down the diagonal and 0 everywhere else. So think of this as you're going to have, if this is a 2 by 2, you're going to think of this as going to have lambda down the diagonal and 0 everywhere else. So when you do A minus lambda I, you are going to be taking and subtracting lambda off the diagonal, because 2 minus 0 is just 2, 3/4 minus 0 is 3/4. These diagonals don't change, but the main diagonal is going to have a lambda subtracted off of it. So we're going to have minus 5 halves, 3/4, 2, minus 5 halves minus lambda, 2, 3/4, and then we're going to have minus 2 minus lambda. So again, we subtracted lambda off the diagonal, and we end up with this. Now, this is actually finding the determinant of this. So let's go ahead and find the determinant of this. The determinant of this is, again, you multiply down the diagonal and multiply the other way. So you're going to have minus 5 halves minus lambda times minus 2 minus lambda minus 3/4 times 2. So you multiply down y diagonal and subtract the other way, and that's going to equal 0. So notice first off, you get a nice equation, and we can actually solve for lambda. So we can go ahead and find what lambda is equal to, and it turns out lambda is equal to -1, and lambda is equal to -7. What we now need to do is find the eigenvectors that correspond to each of these eigenvalues. So let's take each one individually. Let's take lambda equal to -1. And that means, again, we've got A minus lambda I times K. Well, A minus lambda I will be the A, which is minus 5 halves minus 1, 2, 3/4, and then minus 2 minus a -1. Because we're subtracting the -1 out the diagonal times k. What might help to write what k is equal to. So let's actually think of what k would look like as a matrix, because we are doing some multiplication here. So let's call that k, k1, k2. So k, and we'll call this one k1, is the matrix k1, k2. All right, so negative 5 halves minus 1 is let's see, negative 5 halves, minus a negative 1. Whoops. So it's minus a negative 1. So it's minus plus. So it gives me negative 3 halves, 2, 3/4, and negative 2 minus a negative 1 is going to be negative 1. So now we can go ahead and multiply these together. When you multiply matrices, you're going to get negative 3 halves times k1 plus 2 times k2. And 3/4 k1 minus 1 times k2. And that equals the zero matrix. And again, the zero matrix just means you have 0 everywhere in your matrix. Since this is a 2 rows and 1 column, this will be a 2 row and 1 column of just zeros. Matrices are equal if their corresponding entries are equal. So negative 3 halves k1 plus 2 k2 has to be 0. 3/4 k1 minus k2 has to be 0. Great. So this means that k1 is equal to 4/3 k2. And this one also says that k1 is equal to 4/3 k2. Well, that doesn't look like it helped me very much because we basically have the same thing. We can't find out what k1 and k2 are, but we can because we can pick. We can actually pick something to let either k1 or k2 equal, and then find the other one. So let's let k2, in this case, you can let it be 1, but then you're going to have fractions. So I don't like fractions. I try to avoid them if I can. So I notice if I let k2 equal 3, then k1 equals 4. So this eigenvector, k1 I called it, is the matrix 4, 3. We're going to do the exact same thing for the lambda equal to negative 7 halves. So we're going to do a minus lambda I times k, and that's going to equal the 0 matrix. So we have, again, my a was negative 5 halves. So negative 5 halves minus 7 halves is positive, minus a negative 7 halves is positive 1. And then we're going to have 2. And then we're going to have 3/4. And then we're going to have, remember we had negative 2 minus a negative 7 halves. And minus 2 minus a negative 7 halves is 3 halves. Okay, so we have this matrix. This again, we're going to call K2. K2, you can call these something different if you want. You can call them K1, K2, you can call them K3, K4. It doesn't really matter because they're not important in the final answer. And this is going to equal 0, 0. So again, K3 plus 2K4 has to equal 0. 3/4 K3 plus 3 halves K4 has to equal 0. So K3 is equal to minus 2K4. Same thing with this one. That would give you the exact same answer. K3 is negative 2K4. So they work out the same thing. You're going to get the same answer from them. They are a dependent system. They will give you always the same answer. And again, what I'm going to do is pick one of the values for one and find the other one. So in this case, it makes sense to let K4, in this case, I can let it be 1 because then I got K3 equal negative 2. I don't have fractions. I don't have to worry about it. You don't want to let it be 0 because then you get 0. That's boring. But you want it to be something like 1 or something. You can be negative 1 if you want this one to be positive. It doesn't really matter. That does tell me that you won't get the same answer as everybody else because you may pick different values for these, but they are linearly dependent values. So that's why it works out nicely. So K3 was -2, K4 was 1. So the matrix K2 is -2, 1. So now I can write my solution. My solution X is equal to C1 times X1 plus C2 times X2. X1, if we come back here to where we were kind of at the start of all this, looking at this, we said that e to the lambda 1t times k1, e to the lambda 2t times k2, all the way on. We only have 2 of them, so we only need to work about these 2. So if we're using the lambda 1 of -1, then we need to use the k1 that belongs with it. If we use the lambda 2 of -7/2, then we need to use that k2 that goes with it. So this is going to be C1. So we still have constants because this is not an initial value problem. And you're going to have K1. And I'm actually going to write it out just so you can see exactly what's happening here. So we have K1 e to the lambda 1t plus C2 K2 e to the lambda 2t. C1 again is a constant. We only have to have an initial value to find out what that is. So K1 was 3, 4. Sorry, 4, 3. I wrote 4, 3 and said 3, 4. E to the negative t, because lambda here was -1. K2, we just found to be -2, 1. E to the -7/2 t. So you can, in fact, draw these if you want to in a system to take a look at. You can see what different solutions would look like. So you can use technology to draw what the system looks like. You can see that these are the equations that come up from it, and you can see how it all fits together. All right. I should make the comment, by the way, that if the lines go to the origin, we call them, if they go to a point, we call them an attractor. So all the lines go to a point. And we call it a repeller if the lines go away from the point. All right, let's try one more of these and just see kind of what it looks like, just to make sure you've got this down. Oh, no, we won't. We're going to do case 2. I'm going to stop the video to do case 2, but I do actually want to stop sharing for a moment and see if I can't. Give me a second. So I'm going to go ahead and draw these up on my iPad to show you what these look like again. And so we'll do the one we just finished doing. All right, so what I need to do is I need to remember what my values were. So we had the matrix -5/2 x plus 2y. So I'm going to type in -5/2 for my x coefficient. That would be -2.5. And then my y was 2, has a coefficient of 2. My next equation was 3/4, which is 0.75. And then the y there has a coefficient of -2. And this is what it looks like. Notice when I look at this, I see all my arrows kind of heading towards the same place. They all look like they're heading down towards some point. This means that this actually is a attractor, or what we sometimes call a sink. So you can also call it a sink because they're coming to that. I can go ahead and solve one and just show you kind of what it looks like. If I were to pick one initial value point, let's say that one there, you can see that this line goes along, comes down and heads to 0. And I know it's heading because my arrows are all heading in that direction. We're all heading towards 0. Notice the graph does look like an exponential. We have the X and the Y on there. So looking down here, you can see you have your X's and Y's. Sorry, I didn't keep moving things. And remember, our equations were had an e to the negative t and e to the negative 7 halves t. And notice as x goes to infinity, these would be going to, or t goes to infinity, these would be going to 0. And you can see that these graphs do in fact kind of say the same thing that we saw in our solution. So this helps us see this. If I were to change my coefficients, so let's say I change my coefficients to, let's say 2 and -7 and 5 and 40, I believe. Can't read my own handwriting. Then if I clear this out, we see a totally different thing happening here. All my arrows are going away from my origin. They're all going away, which means that we have a repeller, or we sometimes call a source. This is where it's starting and it goes off from there. So we have these different ideas we can have. There'll be other videos that will show you what we do when we have repeated eigenvalues and complex eigenvalues. So this is the end of this one, but there are other videos that show you the other ideas. But you can graph any of these on your graphing, on your any technology that we have, and this will show you what's happening. So again, this one is a source. So another way we can use here, instead of saying sinks, instead of saying attractors and repellers, we can call them sources and sinks. So attractors would be sinks. Repellers would be source. This is your source and everything goes away from your source.